Hello, this is the second in a series of presentations about hyperbolic functions. In the first presentation, we looked at the origin of hyperbolic functions, their definitions, and various identities that connect them. In this presentation, we'll look at sketching the main hyperbolic functions and then derive expressions for their inverses. Let's start by sketching sine x. We'll define y equals sine x, which is equal by definition to e to the x minus e to the minus x on 2. This curve crosses the x-axis when y equals 0, i.e. 0 equals e to the x minus e to the minus x on 2. Multiplying both sides by 2 and e to the x and rearranging gives e to the 2x equals 1, i.e. x equals 0. Differentiating gives dy dx equals e to the x plus e to the minus x on 2, which is equal to cos x. Note that the gradient is equal to 1 at x equals 0, and the gradient is positive everywhere. The function is monotonically increasing. Next, observe that sine of minus x is equal to e to the minus x minus e to the x on 2, which is equal to minus sine x. In other words, sine x is an odd function. What happens when x becomes large? Well, as x goes to infinity, e to the minus x becomes small relative to e to the x, so y tends to e to the x on 2, which tends to infinity. As x approaches minus infinity, e to the x becomes small relative to e to the minus x, so y tends to minus e to the minus x on 2, which tends to minus infinity. Putting these together gives the following sketch for y. Don't forget to label the axes, origin, and the curve itself. Now let's do the same analysis for cos x. This time we define y equals cos x, which is equal by definition to e to the x plus e to the minus x on 2. To find where this function crosses the x-axis, we set y, which is e to the x plus e to the minus x on 2, to 0. Multiplying by 2 and e to the x gives e to the 2x equals minus 1, for which there is no solution. In other words, the function does not cross the x-axis. Next, we note that y of minus x equals cos of minus x equals e to the minus x plus e to the x on 2, which is cos x. In other words, cos is an even function. Now thinking about the gradient, dy by dx equals e to the x minus e to the minus x on 2, which is sine x. As we've seen above, sine x is only 0 at x equals 0, so the gradient is only 0 at x equals 0, and by calculation we can see that cos of 0 is 1. Finally, as x goes to infinity, e to the minus x becomes small relative to e to the x, so y tends to e to the x over 2, which tends to plus infinity. Similarly, as x tends to minus infinity, e to the x becomes small relative to e to the minus x, so y tends to e to the minus x on 2, which tends to plus infinity. Putting this together gives the following sketch for cos x. Again, don't forget to label the axes, the origin, and the curve itself. Now we sketch tanh x. Let's define y equals tanh x equals sine x over cos x equals e to the x minus e to the minus x over e to the x plus e to the minus x. This crosses the x-axis when 0 equals e to the x minus e to the minus x over e to the x plus e to the minus x. The denominator is never 0, so this equation simplifies to e to the x minus e to the minus x equals 0. In other words, e to the 2x equals 1, and x equals 0. As we've seen, the derivative of sine is cosh, and the derivative of cosh is sine. Therefore, we can use the quotient rule to differentiate tanh. So dy by dx equals cosh x times cosh x minus sine x times sine x over cosh squared x. But in the first presentation, we met the identity cosh squared x minus sine squared x equals 1. So this derivative simplifies to 1 over cosh squared x. Note that this is positive for all real x. The function is monotonically increasing. Note also that the gradient is 1 at x equals 0. Finally, as x goes to infinity, y tends to e to the x over e to the x, which is 1. Similarly, as x goes to minus infinity, y tends to minus 1. So y equals plus or minus 1 are asymptotes. Putting these facts together gives the following sketch for tanh x. On this sketch, we should mark on the asymptotes y equals plus or minus 1. Now we'll look at expressions for inverses of the main hyperbolic functions. If y equals sine x, which is equal to e to the x minus e to the minus x on 2, then x is the inverse sine of y. In other words, we need to rearrange 1 to make x the subject. From 1, we have 2y equals e to the x minus e to the minus x. Now multiply by e to the x and move everything to the right-hand side to give 0 equals e to the 2x minus 2y e to the x minus 1. This is actually a quadratic in e to the x. Setting z equals e to the x gives 0 equals z squared minus 2yz minus 1. And this can then be solved using the quadratic formula to give z equals 2y plus or minus root 4y squared plus 4 all on 2, which simplifies to y plus or minus root y squared plus 1. Now one of these roots is positive and the other negative, but z must be positive because e to the x is positive for real x. So therefore, e to the x is equal to y plus the square root of y squared plus 1. And consequently, x is equal to the log of y plus root y squared plus 1. And that's equal to the inverse hyperbolic sine of y. Changing variable names gives inverse sine of x equals log x plus root x squared plus 1. The computation of the inverse cosine is similar. If y equals cosh x, which is equal to e to the x plus e to the minus x all on 2, then x is the inverse cosh of y. So our objective is to rearrange equation 2 to make x the subject. Multiplying by 2 and then by e to the x and rearranging gives 0 equals e to the 2x minus 2y e to the x plus 1. Writing z equals e to the x as before gives 0 equals z squared minus 2yz plus 1. And applying the quadratic formula gives z, which is e to the x, equals 2y plus or minus root 4y squared minus 4 all on 2, which simplifies to y plus or minus root y squared minus 1. So x is the log of y plus or minus root y squared minus 1, and that is the inverse cosh of y. Replacing y by x gives two solutions. Inverse cosh of x equals log of x plus root x squared minus 1, and inverse cosh of x equals log of x minus square root of x squared minus 1. It's not clear what the relationship between these two solutions is. We can make this second result more intuitive by multiplying the numerator and denominator by x plus root x squared minus 1 to give inverse cosh of x is log of 1 over x plus root x squared minus 1. And that's equal to minus the log of x plus root x squared minus 1. Thus the two roots are actually plus or minus log x plus root x squared minus 1. Representing the results like this is nice because it's consistent with us knowing that cosh x is even. In any case, by convention, the positive root is taken as the principal value of the inverse function. The derivation of inverse tanh is the same but easier. While there's an e to the 2x term, there is no e to the x term, so only one solution and no need for the quadratic formula. We conclude with a few simple examples. The inverse hyperbolic sine of 2 is given by log 2 plus root 2 squared plus 1, which comes out as 1.444. The inverse hyperbolic cosine of 3 is given by log 3 plus root 3 squared minus 1, which is 1.763. And the inverse hyperbolic tangent of 0.8 is given by a half log 1 plus 0.8 over 1 minus 0.8, which is 1.099. Each of these can be checked by computing the respective hyperbolic sine, cosine and tangent of the result.